we're going to be talking about today. This type of presentation I've been doing on and off for many years. Called Ignite Pearls, and in a second we'll know why. And I'm sure that most of you probably just heard about Apache Ignite. Maybe some of you actually looked at it and coded it. It's one of the top projects in Apache software foundation. But it's always been a challenge. When Apache Ignite is a very complex software, and I say it with a straight face. It is a memory computing platform. It's a massively highly distributed system with the key value transactions and SQL and a machine learning built in and streaming. And there's a lot of moving parts in it. And there was always a challenge to basically figure out how do I talk to you guys in a 45, 60-minute time frame and really deliver anything other than just basically a routine rundown through the slide deck and with millions of features that you guys forget in a second. So we've always been struggling with this, by the way. I've been doing these presentations for years and years, and it's always kind of struggled to find this balance. So as a matter of fact, the idea came from this book. I mean, one of the famous books from mid-80s by Joe Bentley called Programming Pearls. I mean, any of you older than 30 years old probably would remember that book. That was kind of inspiration for this type of presentation. This book was pretty, when I was in high school, when I was reading this book, it was pretty cool. Relatively to any other books in the same time, it was actually basically just a bunch of essays from ACM publications over the years. And each basically, each chapter in this book was a kind of a combination of a complex problem and a very elegant, short solution to it through an algorithm or a coding or something like that. So the inspiration for this type of presentation came from this book. So what we're going to be doing today is that instead of basically going through a laundry list of kind of hardcore features and whatnot, I'll show you live coding. And there's quite a few things in Apache Ignite that will basically amuse you. How with a few little lines of code, you can get a very unique result. I guarantee most of you haven't touched Apache Ignite. You'll be amazed and surprised what can be accomplished. As a matter of fact, I'm going to ask you to explain how it works. Most of you would not be able to do it. So that's, my job here is to really get you a little bit excited. Come away from this presentation kind of thinking, holy crap, how does it really work? How can you do so many things in just a few little lines of code? And so that's kind of my goal for it. So literally I just have like a couple of slides just to explain very briefly what we're talking about, from Ignite and computation read perspective. And then we dive into the code and have some fun in the next half an hour or something. So what is Apache Ignite? Very briefly, you guys can read this enough. Apache Ignite is a Java-based software. It's an in-memory computing platform. It's typically all about two things: speed and scale. You get speed by moving most of the data in RAM. Obviously, like any other system, we support both RAM and the persistence if we need to spin up, to spill over if RAM is not enough. So you get speed by moving data into the RAM, and you get scalability or scale by massively parallelizing the processing. We're going to concentrate most in the second part. Moving stuff in RAM kind of benign. There's a lot of stuff there. I can talk endlessly, but we'll talk about some of the basic parallelization today and how cool can that be. It typically slides in between your data sources and your applications. It sits there as a layer, and that's practically all you have to know about what it is. Apache Ignite is a very cool project, by the way, if you're not familiar with. It's surprising if you know Hadoop, Spark, Cassandra, it's about the same. We're literally top 5 projects since we joined ASF in 2014. And we were, I think, next to Spark, the fastest growing project in the Apache Software Foundation. We're currently at top 5, depending on the metric, number 2, number 3, number 4. But right there with the Kafka, another awesome project with Hadoop and Spark and Cassandra, all that stuff. So I'm going to be talking about 2 things today. Well, actually one thing and kind of 2 different concepts. I'm going to be showing you mostly a computational grid capabilities. The computation grid essentially is a different name for parallel computing, for distributed computing, and there's a main terminology. The idea, if you're not familiar with what it is, the idea is very simple. Imagine you have a task, and you want to perform this task, and you have 5 computers in the cluster. The idea of parallel programming or parallel computing or distributed computing is very simple. You can take this task, split the task into multiple subtasks into the 5, since you have 5 computers, execute those subtasks in those 5 computers in parallel, get sub-results back, aggregate them back into the final result, and eventually you can execute this original task 5 times faster. If you have n nodes, you're going to do n times faster. That's it. The rest of it is in millions of details and caveats and traps. But fundamentally, all distributed programming, all the parallel processing comes to this fundamental simple idea. Now there's one more slide here that basically tells how is it different from a traditional kind of client-server approach. And it's kind of important to spell out a little bit. Now, these two pictures looks almost identical, right? It's almost like a children's game to find the difference in the pictures, but there's a fundamental difference there. This is basically over here is the traditional client-server processing, right? Anybody old enough from 60s to 70s to 80s to 90s, mid-90s to actually early 2000s, that's our life right there. That's a traditional client-server processing. So the request comes to this node, and this request needs the data from 2 other nodes. What do? We load this data, from database, for example, into the application level. We load data from all the other nodes to this node. We do all the processing here, return result, right? Sounds classical, right? That's what we've been doing for literally half a century. There's definitely millions of problems here. Not millions, but several. There's a lot of parasitic network traffic, obviously, because you're moving data from nodes to one node. Now, what if this node doesn't have enough RAM or capacity to store all the data, right? There's no parallelization of processing. There's a parallelization of the storage. We've had this for years, but there's no parallelization of processing. So, and typically, once you move this data, you get the processing. Once you finish the processing, you typically drop that away. So you basically waste all the cycles to moving data. So, picture on the left almost never happens today, unless you live under the rock or you have a system that was built 25, 30 years ago. So all we do today is this. Again, the terminology, there's many terms around this. One of the classical terminologies is massively parallel processing, or MPP. Even for me, it's always get confused. But that's what you basically hear in the kind of classical literature is MPP processing. What's the difference between the two? So the difference is very much how the processing happens. And again, it is something I'm going to show you today, but now it's not going to go in this complexity. You will know that something's happening underneath on the hood. So the request comes to the node, but instead of sending data or requesting data from a different nodes to you, you actually take the request, partition it, and send the request, sub-request to those nodes that have the data. All right, if you're not familiar with that, let me say it again. When you receive the request, instead of asking for the data, you actually partition the request further and send the computations to the nodes where the data resides. So those computations get executed in parallel, and only what travels back is a sub-result. Sub-results gets aggregated, returned back. This way, there's almost no parasitic exchange of network. There's no movements of data. By the way, data is always bad to move. Data is large, it's changing. Code is small and almost static, right? So you can move code and cache it very effectively. Data you cannot move. It's almost a no-no. So in this case, that's how 99% of any enterprises here in the 5 miles radius will work today. Facebook, eBay, you take any significant system today, they all operate on this principle, right? Obviously, implementation could be very different, but nonetheless. So anyways, that's it as far as just a little background on what we're going to be showing to do today. So what I'm going to do right now, I'm going to drop into the kind of coding. And we're going to start something very simple, and we're going to gradually kind of walk this way into something very interesting. So I'm going to use Ignite. I'm going to code in Scala. I don't know, how many of you guys are familiar with Ignite, first of all? All right, a couple of hands. How many of you guys know Scala? Perfect. So for the most of you, it's going to be pretty cryptic, which is exactly the case. It's very close to Java. If you guys are familiar with Java, Scala, any JVM-based language, it's a verbatim. It's just I use Scala, but that's pretty much it. So let's go ahead. So let me set up first, just make sure you guys can actually see something. So I'm using an idea. I just have an empty project here. In this project, I basically have Ignite library 275. You can download from Ignite from apache.ignite.org. I have Scala pretty old version, but nonetheless. And basically, let's go ahead and start creating some classes, and I'll show you kind of along the way what I'm doing. I'm going to call something Scholar. It's going to be the object in Scholar. And let's make sure that we actually can see it. You guys can see it on the back? Nods? Perfect. So, so to do something distributed, right, we need to have a couple of nodes, a cluster. We're going to call it a cluster. So what I usually do, I run 2 nodes from a command line, and I run a 3rd node from ID, right from this code. So we're always going to have a cluster of 3 nodes. Again, the nodes I'm going to run from a command line, they can be anywhere. It doesn't matter. You can run them from a Docker, you can run them from a command line, it doesn't really matter. It can be in the middle of Siberia for all I care. As long as there's a connection to it, that's all I care. For simplicity, I'm going to run them from my command line. As you can see, I don't even have a network connection here. You don't have to have it. So it's very simple. You just go to Ignite, and it gives it ignite.sh. I'm on Mac. Just give it a command line. I'm sorry, the configuration file. It starts up. It's all by default. I didn't change anything. So by default, it actually use IP multicast discovery. Obviously, on the cloud, it's a little bit different. You know, we don't have it built to multicast in the cloud, but locally, it's just basically that's it. So if you look at the log, it's very simple. Every time there's topology change, and topology in cluster is basically synonymous. I use the word topology most of the time. You can see this topology snapshotting. Every time topology changes, it fires a topology snapshot. You can see the server. There's 2 servers in the cluster right now. So right there. So this is server 1, server 2. Simple as this. Again, these nodes can be anywhere in the world. It doesn't really matter. As long as there's IP connection to it, you can set up the cluster. You know, many users of Ignite actually set up very heterogeneous clusters, you know, that are geographically distributed. As long as there's connection, you can do it. All right, let's go back here. So what I'm going to do here is essentially create a simple application. And the first task I want to do, I want to make sure that this cluster that I'm actually writing, the node itself, will join the cluster. We'll see if it happens. So something like this, if I'm not mistaken. It's org Apache Ignite Scala. By the way, Scala is a little bit of a DSL for the Scala language itself. And something like this goes. And the way you start is very simple. You basically just use the Scala. You know, by the way, if you're not familiar with the Scala keyword, don't worry about this. It is actually our keyword. It's part of a DSL in Scala. It's very simple. In terms of the programming language, think of it as a function. And whatever's in these brackets will be executed in this function. So the Scala basically, it starts up the node. All we have to do is to pass, really pass a path into the, so what I'm going to do is figure out where's my configuration. And I'm just going to copy it over. So I'm just going to copy this path over here. And I think it's called example Ignite XML. So, and right here, so for now, just to basically just see can we join the cluster. So for now, we're just going to print something like hi. And let's see if it works. So what we're going to do is go over here, say run, and see if we make any mistakes so far. So as you can see, it starts exactly the same cluster. Now, nothing really interesting happened, right? But for a split second, we should have 3 nodes in a cluster. Let's double check if we do have this. So if we look at the topology snapshots on those 2 nodes, so we can see that for a split second, we have 3 nodes. Obviously, we didn't do anything. We just did a print out, and there's nothing else. And we're back to 2 nodes. So that our node over here simply just joined topology, became a 3rd node in the cluster, did nothing, and exited. That's all we did. But at least that's how easy, quite literally, to create a cluster. Now let's do something interesting. Let's beyond just say hi, do something a little bit more different. So let's do just a series of exercises where each exercise will basically go a little bit or more. Let's for now just print out topology. Just print out every node we have. So we can do it pretty easily. It's called the Meetup topology. It goes something like this. In Scala, again, if you're familiar with Java, it looks exactly the same. And we're gonna learn something new here, and it goes something like this. And what we're gonna do is we're gonna print, and we're gonna print out essentially just a node ID, and it goes something like this. And instead of this, we're gonna call the topology. So let's run, and I'll explain what's happening here. Although it's pretty self-explanatory in this case. Let me just see if I can make it a little bit bigger. So what we have here essentially, we're calling a function that just prints out all the IDs of the nodes that in the cluster, right? So the only interesting part here is this little thing over here, and you're going to see it a lot down the road in our further examples. Essentially, I don't want to confuse it too much, but think about this. The Ignite has a very functional APIs, although it's basically based on Java. We still have a Java APIs. It's a very functional. So Ignite with the $sign, but the $sign is just a syntactic sugar. You know, sometimes we have conflicting names between Java and Scala APIs, and when there's a conflict, we added the $sign to the basically suffix, so we don't confuse them too much. But fundamentally, Ignite essentially is a monad, is a monadic projection on number of nodes. So we have exactly the same set of operations that are available on one node or on a group of nodes. And you're going to see this a lot. So when you see Ignite keyword essentially, or that's a function in Scala speak, it basically means one or several nodes. It could be 1 or 1,000 nodes, 2 or 3, or any other dimension. So what I'm doing essentially is saying, hey, give me all the nodes, iterate over each of them, and for each of them, print out the topology. All right, so that's pretty simple. You know, we just confirmed we have 3 nodes, which is not surprisingly, that's what we have. So let's go further. Let's do something else. Let's actually do something that is, well, let me write it. You guys follow it. We're gonna create a function called say hi. And that's going to be a little bit different. Now that this function will actually instruct other nodes, including this one, to print something out. Now, let it sink for a second, because we're going to use that throughout the rest of it. From this node, we're going to instruct other nodes to perform some operations, which I will encode here. Those nodes in the middle of Siberia, they have no idea what I'm doing, right? But I will somehow instruct them to do an operation that I need to do. Now check this out. It literally takes exactly. So we're going to use a broadcast call, and I need to give it a essentially a closure, and the last argument is a filter. It's basically a predicate on the node. We don't need any predicates, so fast to know. But over here, we're just basically doing the same thing and saying hi. As simple as this. And we can actually get a kind of node ID here. There's a bit of a function here that you guys, you don't have to really do this, but we can just say cluster local node and get ID, and we can say something like this, so that we know actually which node says hi from, and pass the node ID. So let's give it a shot and run it. Okay, let me run it. Let's see what happens, and then we're going to actually kind of work this through a little bit. Same way, just run. Fortunately, it doesn't remember the size. So okay, so now if you look this on this node, we can see it right here. It says hi from actually local node. This is the ID of this node. It says hi. You guys don't see it, but it says hi from actually this node. And back here, it's also a node, exactly the same as the other nodes. It says hi from actually this node. Sounds simple, right? Kind of trivial. Now let me ask you the question. Did you guys see any deployment steps?
No.
Do you see me copying anything? Starting, restarting, packaging, running anything? Just scroll back what I've just did. Done. I've been writing this code right here. It's a local ID, doesn't matter, notepad. I don't care what it is, it doesn't have nothing to do with the ID. I run this code, I started it, and all of a sudden, the other nodes on the other side of the planet knew what to execute. As a matter of fact, there's nothing here magical. I can basically change this, and any way you like it. I can say, hello, run it again. And it basically says here, hello, and if you go back to our nodes, it now basically says something else. This basically says exactly what we say, hello with exclamation point. So this is one of the awesome things about Ignite. And I can explain a little bit what's happening here, but it's a very complex technology. We have what's called a kind of zero deployment. It's a very complex machinery around a standard Java class loading on demand. And I can probably talk about it in hours, but fundamentally, what you get is that level of simplicity and a bit of a magic. Because this is actually very simple. The further examples will be actually a lot more kind of fascinating what we can do at it. But think about this, that's how simple you can actually do the traditional RPC or any kind of remote procedure calls, if you like, to a cluster of computers. Exactly the same code works in one node and two nodes or dozens of nodes. We actually have Microsoft Azure and authentication system is built on Ignite and GridGain, and they use this capabilities on hundreds upon hundreds upon hundreds of nodes in topology. So let's move on. I think we have kind of crescent time. So let's do something very traditional called the hello world.
Question.
Sure.
So if that runs in master and the slave mode, there's no any this kind of concept?
So the master and the master and the slave is illogical. So whenever task on whatever node the task starts, for that task, this node will be the master. But we don't have a concept of a master or a slaves. It's a very homogeneous structure. It's a bunch of nodes floating, right? And you can connect to any node, but there's a provision to know how to figure which one is not. But when you start a task on a node, for that particular task execution, that node becomes a master, and everybody else can become slaves. But master and slave is a logical for us. There is no specific master. There's no specific node. There are client nodes. For example, when you connecting to this cluster from externally, right? If you like to, from Python, from Node.js, from .NET, from C++, we have many clients. Then those nodes are very specific. But the cluster itself, when you perform operations in the cluster, they're homogeneous.
So in the clusters, actually, any nodes can send out the request to the other nodes.
That's true.
Okay.
That's true. And you can limit this. I don't want to go into details right now, but you can obviously be very specific how you limit this. There's all this kind of functional operations. You can basically limit this node can only execute, this node can only send, but those are logical things. There's nothing pre-built for it. So let's do a hello world. And a hello world and distributed world is a very simple thing. Instead of printing the hello world, we take the hello world or whatever the phrase, we split it by words, and each node prints individual words. So it's a little bit of a play on the same idea we had before, but it goes the same way. A little bit, a little bit more involved. So what we're doing here is we're going to use a different method called run, and run takes a sequence of closures. We can get them basically in different ways, but one of the ways I basically usually do is this. We take this, split it by spaces, and let's say something like hello Ignite world, and we split it by spaces, so we get a bunch of subwords, and we convert that on the exit into the essentially the same thing. Pass the null here, and that should be it. So let me just move it a little bit faster there. So very much the same like the previous one. The run itself is a little bit different function. So the run itself takes a sequence of closures, right, and it spreads them over the cluster. So we have, I know it's kind of made up. I have 3 closures because there's 3 words. I know there's 3 closures, 3 nodes. Each node will print out basically 1 word. But let's see if it works. So I hope you guys getting the sense of how cool this can be. Those are very trivial examples, right? I'm just showing you what can be done. But imagine what can you do in real life with this type of capabilities. And we've seen obviously in Apache Ignite community, we've seen very cool examples of how this stuff works. So let's see if it works. All right, so this node printed hello. Obviously 2 other nodes print Ignite and print the world. So that's pretty cool. I actually remember when I was the guy who developed this whole machinery many years ago. And I remember then when we achieved that level of abstraction and simplicity, that was a wow effect. You won't find it anywhere. Ignite still today is the only software system that has these capabilities. I know folks from Spark, from Flink, from other like Hazelcast and Gigaspaces, from in-memory systems. None of them have these capabilities, and that's how simple it is. And when it comes to in-memory computing, simplicity, weighs in gold because it's complex stuff. And anytime you can simplify certain things in it, that's a big deal. So anyway, let's move forward. Thank you. There's one guy who knows what complexity is.
If you run that again, will that be random? Which nodes print what?
Not necessarily. It's 3 nodes. But it can be, yeah. At this point, run basically takes some random. Let's see. No, it's the same. Let's do it again.
Depending on the algorithm, how to use for this one.
Yeah, you know what? We can change this one. Why don't we just say Ignite Meetup world. So we're going to have at least now 4 words, so somebody will print 2. So this guy now got Ignite, and somebody else got 2 words. Yeah, this guy got 2 words. World and hello, and this guy got Meetup. Yeah. Obviously, by the way, you can control all of that. But that will require extra lines of code. I don't want to bore you with this, but believe me, you can control. One of the things about Ignite, it gives you goddamn too many controls. It's one of the problems with our APIs because you can go nuts with how you control it based on current load of a node, based on any other conditions. You can be very specific in how a distribution works and what happens in terms of the error and the failover and whatnot. But that's actually I'm going to show you the failover piece pretty quickly. So let's do something more interesting. Okay, we'll just keep printing out stuff. But let me actually show you a version of the the world's shortest map reduced version. So we're going to do basically a function that calculates length. We'll get the string, return int, and we're going to do this. We're going to do this essentially in distributed fashion. So very similar again. It's you guys are going to catch this. We call it the reduce. Let me just see what examples I want to show it to you guys. Yeah, we're going to kind of shorten up a little bit on time. So I'm going to show you the reduce. It has a type of int essentially. Again, I'm going to give you a sequence of closures as a first parameter, right? Again, it goes pretty much almost like the previous example. We splitting the given string by spaces. And what we're yielding on the output here is a little bit different. We're basically returning the length of the word. And here we providing a aggregation function. And as always, we don't really care about the predicates here. So that's about it. That's the entire map reduce right there. If you want to calculate this in non-space characters in the string, that's essentially what it is. We're going to modify it a little bit. Let's just check that this works. It works. So let's create some string. I'm going to copy the string from here, so we don't really. So I'm going to call this something like this, and I'm going to calculate and just print right away. So we call a length is, and calculate length, but pass the S into it. So, let's give it a shot. By the way, we're not going to see much because it's just going to return the number, right? We don't know actually what's happening. So right in this closure, what I'm going to do is this. I'm going to print out essentially what is happening. I'm going to say calculating the length for and pass actually what I'm calculating for, right? So at least we'll know who's doing what job. Let's go ahead. As usual, we don't change anything, right? Keep in mind, guys, you haven't seen me once doing any deployment steps, right? That's a pretty cool stuff. So, let's again. So this guy was calculating for Ignite. So remember this. We split the work, right? Remember this, the slide number 4 showed you in the beginning, right? About the actually MPP processing, where I'm sending the computation somewhere. This is what's happening. I send the computation, well, this is local node, right? But let's take a look at here. So this guy will calculate the length for hello and for world. And this guy was calculating the length for the meetup. So obviously, these things can be, again, let me repeat this. These nodes can be anywhere in the world, and that's how easy you can essentially instruct them to do some work for you. There's literally no instruction. By the way, I didn't mention this, but did you guys see any networking code, any failover code, any marshalling, demarshalling, class loading, none of that? That's the beauty of this. I mean, it may sound kind of trivialized a little bit. It is. It's just a pure examples of what it can do. But think about what it would take you to build something like this without that tooling. It will be hundreds upon hundreds of code if you just do it once, right? With all the networking, the marshalling, demarshalling. Let me actually give you another example. Look at this variable W. It's going to blow your mind right away. So this variable is created in this node. But this variable is actually used to print out itself on a node 1,000 miles away. Let it sink for you for a second. These 4 lines of code, don't care about the language, don't care about syntax. This is the variable W, right? It's a single word. This piece of code executes on this node. That's where I'm doing the split. It's actually simple Java code. I split it by space. I get the string, I split it by space. I create this variable W. But then in the very next line, I use this variable, and this is a closure, right? This is the curly brackets, the closure that sends over. This variable will be used to print out itself on a different node.
So can you rename W to?
No, you cannot rename because it's not going to compile. If I put like 1,
I mean, they still have the dependency.
Exactly. Yeah.
Okay.
And that's for anybody who is not familiar with intricate details of class loading in Java, that kind of blows your mind. How the hell is happening? How the hell does this node remotely knows about my variable I just created here? I just created it. And all of a sudden a different node over there knows about my variable. It is pretty cool. Believe me, when you think about it more, right? I know you guys are not familiar with Scala. That kind of confiscates us a little bit. But when you think about it, this is basically pretty magical what's happening here. You actually have a local programming model that is completely distributed for you. You don't really care of where, what. You basically just say, hey, here's my projection on topology, bunch of nodes. Here's my closure, execute it somehow, or somewhere, or do reduction, or do anything you like. By the way, this reduce code is pretty cool, right? You supply me a bunch of closures, supply me the function. That's the beauty of Scala, by the way. That's how cool is that. Basically, each closure here returns the int, the length, right? What's my reduction step? I just need to sum it up, right? In Scala, it's pretty cool. You basically supply the function sum that works in any sequence in the list, and that's all there is to it, right? Anyways, let's move forward. It's pretty cool stuff there. Let me show you actually.
Question.
Yeah, go ahead.
Could you show the previous screen that says calculating length for Ignite?
Whether-
I think I saw like the length was 23.
Yeah,
That's correct.
For all the characters. And
Yeah.
All the characters.
minus space, yeah. Minus spaces. So it's basically,
Not
we can calculate spaces too. I just specifically did it.
Not use space.
Right.
Yeah, just split it by spaces. You know, when you split by spaces, remove the spaces. So we can basically do any kind of split you like, and the length will be the correct one. So let me show you the failover, because it's probably one of the questions anybody would ask. You know, how the hell the failover would work here? Something very quick. What we're gonna do is just essentially copy this stuff over here and put it in a loop, and we'll start killing machines. See how that works. So something like this, and just to make sure we're throttling it, just something half a second. All right, should be fun. And call the failover. Go. So what we're gonna see basically is exactly the same function. Keep running, keep running, keep running, keep giving us the same results, right? So length 23, 23, 23, go here, same stuff. Check this out. Go ahead and note, press Ctrl-C. Kill it. What happened? Nothing. If you go back into the here, result's still 23. What just happened is that it's automatically, obviously, detected the node is gone, and it reshuffled the mapping automatically for you, and now basically it goes to the other nodes. So we only have 2 nodes left, so obviously we have 4 words, so this guy does the 2 words, and this guy left out does 2 words too. Well, what if we kill this one?
So there's no way to notice to us. There's already have some nodes. It's dying.
No. Look at this. Right now, there's no nodes, only this node.
Right.
The other 2 nodes are killed. That's okay. The cluster of 1 node is still a cluster.
Right, but it's actually, so I need some, maybe some server can monitor how many nodes currently.
You obviously can, yeah. You can do it with Kubernetes, you can do it with all the different
Okay.
things. But from our perspective, we don't care. As long as they have nodes, you know, we will either automatically do this rebalancing, or you can do it obviously manually. But check this out. So this node now working. What if we want to dynamically add nodes to it? Go ahead, add a node. Same node, nothing to do. It automatically picks up the work right away because we have a master node here that actually does. And this node now does less work. So we can go back, pick this node up as well. It's up, and it's automatically going to join it. And there you go. You have back to the same situation. Now this node does either 1 or 2. And these 2 nodes actually are sort of operating. So, Tatiana, what time do I have?
Can you scoop out some?
I mean, okay. You know what? I'm going to skip the last example, which, if you have any questions, I want to, leave the time for the next presenter. Yes, go ahead. Just about any questions, I'm more than happy to answer. Go ahead.
You sent a string essentially over. Can you send any arbitrary object without having to do any extra code?
Absolutely.
So automatically marshals
Yeah.
anything.
Yeah. String is just a basic example. I don't want we can create case object and send the case object for it. As long as the object can be normally marshaled or demarshalled. So that's a little bit, you have to be careful about what's inside of it, like transient fields, how it get initialized, all of that. We can actually send, a very complex object. For example, we can send the BBC drivers, or not the driver itself, but the context. Anything that can be safely demarshalled, we're going to automatically demarshal it for you. That actually opens up a tremendous amount of capabilities, what you can do. Again, think about this. They still like a very trivialized examples, but trying to project on your task you have, what you can do with this. And I know for many years I've been doing this, for more than a decade. We've seen a tremendous amount of examples where obviously not 3 lines of code, but something that is a little bit more involved, actually runs a complex production systems in financial services and in healthcare and whatnot. Very much based on the same principles. You literally, with a few lines of code, you can distribute your tasks anywhere. Those tasks can be anything, right? Think about this. This closure right here, when we're calculating this, a little bit of a map-reduced function. This closure can be anything. It's whatever you like it to be. You can calculate Monte Carlo, you can print out something, or you can basically do millions of lines of coding. We have customers and users of Apache Ignite where this closure essentially calls out the old COBOL or Fortran, C-level bindings. And that's the beauty of this, Fortran and COBOL are not distributed systems, but if you add them here as the last mile computation, you can make your existing COBOL and the Fortran code on the mainframes fully distributed. And possibilities are endless there.
Question.
Sure.
So how the network affect to performance?
It does. So, because obviously, well, it does in a minimal way. Well, one of the axiomatic things within Ignite or GridGain is to minimize data movements. But we cannot change the laws of physics. You cannot make them completely disappear. So we have to move data, mostly computations. So that's why it doesn't really matter if you have, a 100 gigabit network. We're perfectly fine work on 10 gigabit network or even less. But when it comes to a data distribution, which is a major part of Ignite as well, their network really matters. It does matter specifically on the large, heterogeneous deployments where you have a local cluster and you have basically a cluster spanning geographical areas, like over VPN. Then it becomes, I wouldn't say problem, but a consideration, because we're going to be working as slow as the slowest latency on slowest link in your topology, because we have to count for kind of heartbeats back in, going back to us. So it is a consideration. It's typically not a problem. For us, for many of our customers, the problem typically comes from a data sizes, because in memory computing, although we support full persistence, by the way, on the data grid side, it is typically a problem in modeling how much RAM you have versus how much disk or flash you have, because these systems are not good for petabytes. If you need the petabytes, go Teradata, go pick up Hadoop, do something else. If you have tens of terabytes or less, that's the prime use cases for us. 5, 10 terabytes, we do it day in and day out. And you can do it in one of the largest cluster we have, really measured in a few thousand nodes. So we understand the scale, the system is really built for scale, and we have production customers with that scale running on this. So you can do quite interesting things. And again, kind of in conclusion, what I really want you guys kind of remember and understand. I know it's Scala, you're not really familiar with it, so it may be confusing. But remember how simple it is. Think about what we accomplished. Think about, pick up a different framework and think, how would you accomplish the same things in a different way? Try to build this, benign calculation of length in distributed fashion. Just from scratch. Pick up your favorite language, doesn't matter what it is. Try to build it. Try to make it robust, a failover. Try to make it scale properly when node goes up and down elastically. You can do it. If you're good engineer, it will take a few days. You can do it, but it will be hundreds upon hundreds of lines of code, and that's going to be a challenge. And this is a production-ready system that takes 3 lines of code. It's not a gimmick. It's not a demo. It's actual real code. Most of your code, when you're running Ignite, will be exactly that. Just this closure right here will be something useful for you. But the rest will be very much the same. Yep.
So that's a possible Linux cluster, actually some nodes dynamics to join and disjoin the cluster. I mean, it's actually suppose initially they have the 10 nodes in the clusters running, and later so actually you need to add more.
Not necessarily. That's the easy way to show it. But you can also basically connect to existing cluster from external point. We have clients, so-called clients. For example, you can have this cluster running. If you like, I don't know, if you use Python, you connect from a Python and supply the job to Python. It's a little bit more awkward because you basically have to connect to it. It's a little bit more prep work, but you can do it obviously. You don't have to be in the cluster. But if you want to get maximum performance and kind of ease way, you have to be on the cluster. And obviously, from a production standpoint, nobody runs the code in production like this, right? You debug it this way, you test it this way, but once it's ready, you package it properly and it runs in the cluster as normal. But if any of you guys work in distributed systems, 99% of the time, it's testing and debugging. That's where you spend the time. because that's usually takes, I grew up in the world of, platform computing and whatnot, back in the, mid-90s and early 2000s. My job was like this: I write the code, then I run the make, run the test, and go to lunch. I come back from lunch, my deployment is ready, everything is cool, I can press a button, run the test. I see the error, 2 hours later, I got another one. That was the job in life with distributed programming, literally about 15 years ago. Because that's what it usually takes. You have to repackage, re-download, restart everything. Typically, that's where the idea of Ignite really came about, because it was so ugly, so ineffective. And back about 15 years ago, it was Spring coming up, all this, Ruby on Rails coming up, all these new frameworks, right? It was extremely easy to use. Like literally, you can feel it on your fingertips how easy it is. And then you look at the background of distributed computing, and it was like freaking Stone Age. And that's the idea of Ignite, essentially where it came from, to simplify this, to really give the same kind of appearance and experience that you can very effectively, very easily develop something complex without actually doing something that is unnatural.
So if we're going to use this, Ignite can handle the situation like the Kubernetes, like the handle.
Yeah, we fully Kubernetes, we fully Dockerized, we run on every cloud, there's images everywhere. So from a deployment perspective, you can do whatever you like. Well, whatever you like typically means today you can put a Docker image, just use a Docker for the nodes. Production uses Kubernetes is a good one. We run on AWS, we run on Azure. We have actually images on both of them. We are on the marketplace in Oracle Cloud, Azure, and AWS. So we're everywhere, believe it. You cannot be successful today without having all those keywords in your belt, because from a DevOps perspective, everybody is, using some of them. So we have it supported. So guys, thank you very much. Please look at Apache Ignite. Do it yourself. Try not to steal any course.
What other languages do you have that support something like that? That was Scala, right?
That was Scala. I used Scala for the last 7 years.
I'm just asking what you got to do with this trip.
That was very much same.
Okay.
It was very, very easy. The Google will only say the copy is the same. We have plans, but that is very much the same. That meant we're doing it very much.
I probably like to just be able to handle it.
So I like to use Scala because it's very much the same. I don't worry about all the yeah, you obviously put in so that you get all kinds of callbacks for the payload. You can basically you can rerun the operation, you can cancel the operation, change it a little bit, send it over again. Yeah, all this kind of good things. That's the kind of that's kind of your
So it'll just be
we do all the distributions, the failover, all of that.
Alright guys, our second talk is by Andy, Rivenes Product Manager at Oracle Database and Memory. Before we get to the talk, remember to register for the raffle. That's gonna be right after this talk. We still have food, so make sure to help yourself with a nice dinner, food, drinks, and the raffle are sponsored by GridGain and Oracle tonight. Alright, Andy? The floor is yours.
Hopefully you can see that. So, hello everybody. So my name's Andy Rivenes. I'm a product manager for Oracle. I focus on Oracle Database and Memory. I've actually been here a couple of times and talked about kind of what database and memory is. So I'm not going to spend a lot of time on that. What I thought would be more interesting is actually show you how it works. So I have on my laptop Oracle, it's a Mac, 16 gigabytes, Oracle database running in a VirtualBox. VirtualBox is 12 gigabytes, basically as big as I can make it. The database is running 10 gigabyte SGA for anybody who technically with Oracle who understands what that is. We're running actually a column store and then also in the buffer cache. So the schema that I'm using, the star schema benchmarks, fully cached in both the column store and columnar format and in the row store and row format. So I'll back up a little bit. So starting with database 12.102 and higher, we introduced something called database and memory. It is an option, so you do have to pay for it. It's available both on premises and in the cloud. So in any of the EXA or extreme performance features of the cloud or on premises. What we've done basically is focused on columnar formatted data to speed up analytic processing. So using columnar formats to scan data very, very fast. And the traditional Oracle row format, all of the transaction processing with Oracle database, all of the other options like rack and multi-tenant and data guard, none of that changes. So database and memory is pure in memory. There's no persistence. Any DML changes, inserts, updates, and deletes always occur in the row store. They're reflected in the column store as part of the transaction. So we mark metadata, but we don't generate any undo or redo. When the instance goes down, all of the data in the columnar format goes away as well. So that's the in-memory part of the computing. So that's kind of, if you go back, and I think we probably have my sessions from, I think it was in May, and then maybe at the beginning of the year, I did 2 different sessions kind of describing how all that works and with PowerPoint slides. And so today, no PowerPoint at all. So an Oracle guy not doing PowerPoint. So, you know,
Wow.
you have a miracle for, yeah, exactly, wow. So anyways, so what I'm going to do is kind of go through, I've already started the database up. This is running 18C, 19C's out, 12.2 is available, 12.102 is where we started with database and memory. But an 18C database, Enterprise Edition, with the database and memory, the column store enabled. I'll show you a little bit of how that's done. The takeaway is you don't really have to know any of this, because once you populate objects in the column store, you just run your SQL. So your SQL, your application SQL doesn't change. And I'll show that to you as well. So underneath the covers, we'll talk a little bit about it. The optimizers, the cost-based optimizers, what chooses at parse time, do we access the column store or do we access the row store? Which is also why you don't have to change your SQL, because if you have mixed workload environments where you're running OLTP and reporting, that all can run without having to change anything, which is kind of the cool part of it. So let's see if we can do this. I keep, my mouse keeps going down below, and so it maybe will lock my screen. We'll have to undo that, but we'll give it a try. So if anybody's familiar with how Oracle works, we use a shared global area, and in that we have buffer pools and such, and that's where we stuck the column store because it fit within the architecture of Oracle database. So all I'm showing you here is that we have this new area, this in-memory area. It's about 5 gigabytes, and that's where the column store is, if you will. I know this, since this isn't flat, I know this is going to go out on me. But one other thing I will show you, the only thing actually that your DBA types have to do is set this parameter in-memory underscore size. I set it to that particular value so I could get my schema to fit in the column store. I actually also upped the buffer cache size so that we could compare row in memory versus columnar in memory. So we're not going to do any disk I/O at all, and good thing because I don't have much disk I/O on this Mac anyways. But so that's literally all that has to be done to enable database in memory. So the DBA or your administrator can allocate additional memory to the SGA, allocate this in-memory underscore size parameter, recycle the database, and you're good to go. That's all that has to be done. So it's fully integrated in the Oracle database. So what I've got is a star schema benchmark. Get that off of the web, it's open source. And we have our basically line order table, which is the fact table, it's the large table. We have some dimension tables. We're just going to run some queries against this. For anybody that's Oracle aware, I've enabled it so that it will cache the tables in the keep pool, the row store part of it, and then enable it for database in memory, literally an alter table command, alter table in memory. So alter table, each of these columns in memory. It's a one-time command until you disable it, and then when the database starts up or when you've enabled it, we'll populate it in the background in this columnar format that I'm talking about. And then I've pre-populated it, so we don't have to wait for it to populate. It is populated by background processes, and it's kept in sync by background processes. So all this occurs in the background, so the foreground process doesn't have to endure any overhead due to population or changes in data. And so all I've done is shown that I've populated these, the status is complete. We do compress the data, vector and columnar data compresses fairly well. Typically we get anywhere from 2x to 20x compression rate. And so you can see all that in Oracle $V views. I don't know how many folks are Oracle familiar, but there are views, so you can go look at all this stuff. It wouldn't be Oracle if we didn't give you lots of information about all the different parts of the database, and it's still true with database in memory as well. So it makes the admin part of the job a little bit easier to figure out what's going on. So the bottom line is we're fully populated in the column store. And that's, I mean, all that's just admin, one-time stuff. At this point, we don't ever have to worry about that again. At least for the life of the instance. And the only other thing I wanted to show a little bit, so is this idea of the column store, that in-memory underscore size parameter that we set. You can actually see that it's made up that column store, and I talked about this in the previous presentations, which I think you can go back and look at, or you can go to our website and look at it. But made up of 2 pools, so you can actually see how full the column store is as well. Because naturally that kind of becomes a question, since we populate the object in its entirety, you can only fit so many objects into the column store. And at some point it's going to fill. So either you got to allocate additional memory or take objects out. If you get a partial population where not everything quite fit, or maybe it all fit and it grew past the size, you can see that in these views. What happens is the query will still run, the application will still run, it just won't run as fast because it'll access the data that is populated in the columnar format, and any other data will go to the row store to get it. So your applications will run seamlessly. Again, another Oracle thing where we don't force you to choose where data is located. We take care of that for you. So you don't have to remember any of this, but I kind of wanted to give you some background from the admin side. So let's take a look at querying something. So I have a very simple query. We're just doing a max on the total order price from the line order table. That's that big table. Ran in 0.03 of a second, ran very fast. Potentially, it went to the column store to do that. How do you tell? So in Oracle, you can see an execution plan. So for Oracle database, and it'll say table access in memory full. And that's how you know that you did, the optimizer said, oh, it would be the least cost is to go to the column store. I'm going to do table access in memory. And the takeaway there is that that's how all data in the column store is accessed, the table access in memory full. In other words, we're going to access all of the columns within the query for the entire segment of data that you've populated. It's not the column store is not a cache, it's a store. And that's one of the takeaways about database and memory, and the fact that we focus on analytics, because we've made it so that we can scan data very, very fast. Billions of rows per second per core. And I'll talk a little bit about some of the features within the execution plan. I've talked about some of that before. Again, we have lots of information available on our blog at oracle.com if you're interested in how the inner workings work. We also have statistics that can tell us how or what we did in the work of accessing the column store. In this particular case, you don't need to know this, but there's 111 IMCUs or extents within the column store that make up that line order table, and we scanned all 111 of them. So you can get more information as well from statistics to see how much benefit you got from the column store, how much work you might have saved, which I'll talk a little bit about as we go through this. So great, big deal. So we scanned this data in the column store, it was really fast. What about the row store? Because I said, well, I cached all of the data in the column or in the row store as well, and it ran pretty fast. I didn't do the right query though. Talking and trying to type at the same time. So how do we do buffer query?
Question.
Yes.
So when you see this column store and row store, that means you have two copies?
Yeah, essentially in memory. So what happens is the data is always in row format in the Oracle database on disk, and then in the buffer cache where we will cache blocks as we read particular parts of the data. In the column store, for the tables that you alter or enable for in memory, so not the entire database doesn't have to go into memory. You get to pick and choose the objects you want to populate. That data will then be read and formatted in columnar format in the column store. So for those particular objects, they will exist in both a row format and a columnar format at the same time.
Seems like that's memory.
What's that? Well, the memory the column store requires the entire object to be populated in its entirety. In the row store, typically that's not the case, because Oracle database is very efficient at managing, especially for OLTP type workloads. Typically you have a very small number or amount of data in the buffer cache as opposed to the size of the entire object, because typically we're not looking through the entire object in OLTP environments. So this is why this is analytic focused. Does that make sense? Yeah, that's the design. So that query took 9 seconds. So the same exact query, except notice that thing right there, went from 0.03 of a second to 9 seconds. Same data, same query, except I did put a hint in that told it no in memory. So don't go access that data in memory. And then the execution plan says table access full. Not table access in memory full, table access full. Now, the only reason the hint's there is so I can show you the difference. So in theory, we didn't do any I/O. That's the difference in the efficiency of the row format in the buffer cache versus the efficiency of the columnar format in the column store. Or almost an order of magnitude difference in performance. And if we look at our statistics, we don't have any, and actually, I'll just do a list for that. I actually said, are there any physical reads in here somewhere? Here we go, physical reads. Do we do any physical reads? And in this case, we did not. So we actually did something we call session logical reads. In other words, we only accessed the database blocks for the row store format in the buffer cache. So it was a memory to memory or apples to apples comparison of row-based memory versus columnar-based memory. Pretty amazing in the differences in the speed of it. And that's where I usually tell people I expect about a 10x performance improvement for the same query if it's analytic in nature, if you populate it in the column store versus accessing that data in the row store. 10x performance improvement is what I'm disappointed if we don't get at least 10x improvement. That's kind of the goal. Any questions?
What's the reason for that? Since both of them are in memory.
So they're both in memory, but we have the row format. In Oracle database, in row format, scans each row and traverses each row to get to the column values that are part of the query. In columnar format, we compress that data in its columnar format. We only access the columns involved, and then we get to do things like SIMD vector processing because it's vectorized, it's very vector friendly. So we can do a lot of technical accessing under the covers to make that access of that data very, very efficient, very, very fast.
So if the row has many columns, that would even be faster.
So if the row, if it's a very wide row, then you have potential for even a more significant speed up in the column store, yes. Because we only have to look at the data we're interested in. And we can even further enhance that as well. So one might say, well, rather than doing a full table scan, what happens if we just do an index access? Because typically, for instance, OLTP applications are usually very heavily indexed to make, so that we only have to access the rows that we're interested in rather than having to look through the whole object. So what I did is I have a hidden index, made it invisible, and I have a query with a filter predicate that says go after that key, 5 million, in the line order table, and it runs screaming fast, 600ths of a second. And if we see from our execution plan, we did a range scan because I enabled the index to be used. So in the row store, column store doesn't have indexes, at least not traditional B tree or bitmap type indexes that Oracle normally supports for the row store. The row store does. So for an OLTP application, typically heavily indexed, if you're doing single row accesses or small range lookups, you're going to use an index for that. Of course, the cost is going to be low, so that's probably what you're going to do, even if the data is populated in the column store, which actually in this case it is. So, so that's what you see for an index access. But wait. We have also something, another, not only do we compress the data in columnar format, it's vectorized, so we can use SIMD vector processing. We have something called in-memory storage indexes. So we can run that same query. Now, okay, so I'm going to say that's a wash because we went from a 600th of a second to 100th. So just to say it's just the same, you know, given the variations in this. But the reason that's so fast, and we did do table access in-memory full, is in this execution plan for folks that read those kind of things. We told you that we actually did the filter, but we did it in memory. We took that filter predicate and we pushed it into the scan of the data. So we knew what we were filtering on when we were looking at the data. We don't do that in the row store because we can't. We can do that in the column store. And then the statistics will tell us that, I don't have my pointer, sorry guys, that of those 111 IMCUs that I talked about briefly earlier, all you have to know is that we don't take the segment and put it entirely in memory in one contiguous segment. We actually chop it up like we do database blocks or extents. We have 111 of those. We were able to prune 110 of them out because we knew that only one of those chunks of memory actually had it's only a single row or a single column value, had that value. So we actually pruned it and we didn't have to look through all of the data in this case. We were able to actually just look at a small portion of it, very similar to what that B-tree index was doing in the previous query. So it's all of these enhancements that give us even more speed, which we're on the journey to getting to 10x or better performance improvement. Notice the query is the same though. We didn't change the query at all. So we didn't have to, Oracle under the covers took care of this. We didn't have to change the query. So your current applications, for folks that are running Oracle database, don't have to change to take advantage of this. All right, so scans are great. So, but that's not what typically complex applications do. A lot more than just scanning one single table. So let's take a look at a little bit about. I'm going to skip over to do joins first. This is a session that I actually usually give for a much longer period of time. But let me talk about joins, and then we'll go back and look at IMEs for real quick if we have time. which looks like we probably will. So here's a little bit more complicated query. We're joining line order and date dimension. We're doing an aggregation and with a multiplication there. I hope I ran the right query. Yep, I did. And it ran really fast, 0.3 of a second basically. But now what you see is something a little bit different than what you would normally see with an Oracle database query for the row store. We're doing a hash join, but if you notice there, we did a join filter create and a join filter use. Because the data is very vector friendly, we're actually able to use bloom filters. I'm trying to dig out my pointer. We're actually able to use bloom filters, and we effectively change a hash join into a scan and filter operation on the, in this case, the two tables. So we scan the date dimension table, and we create a bloom filter, and then we are able to apply that bloom filter with the scan of the line order table. So rather than having to go through probing a probe table into PGA, which is what a traditional hash join would do, we're able to do the actual join as a filter operation during the scan of the line order table. So we just went from, we just added another 6 to 8x performance improvement by changing a traditional hash join into a scan and filter operation of the two or more tables in the hash join. So that's a further improvement, and that's an optimizer decision. So that's actually the optimizer that's controlling that. So given that we have a filter predicate on the date dimension table, we can create a bloom filter and actually filter out enough rows to create a, we can filter out enough rows to create a dense enough bloom filter or a memory array to then push that as a filter predicate into the scan of the line order table. And we can do this for multiple dimension tables, if you will. So think star schema. If you had, and this is a star schema, if we have 4 or 5 dimension tables, we could actually scan all of those tables and perform the join during the scan of the fact table without having to do multiple levels of probe table access. Pretty significant in speed performance. So again, analytics. So this isn't typically what you're going to worry about for OLTP, but mixed workload environments and business intelligence environments and data warehouse environments where you're doing significant reporting, this can provide a huge speed up in performance. Now, what does this look like in the row store? So that took .3 of a second. I think I said that earlier. So if we do the same query in the buffer cache, it's going to take a while. So the only difference in the query is this hint. It says no in memory. And this is a great way you can experiment with it. You can download Oracle database off of the developer days in a VirtualBox and do exactly the same thing if you want to try to play around with this and look at it. So this is just on my laptop. Think if you had terabytes of data that you were trying to scan looking for information, how significantly faster that would be, because Oracle database supports parallelization, it's CPU memory access, so now you can go even more than 10x, orders of magnitude faster performance when you start to scale this up. So that took 10 seconds to run, and
How can notice the buffer join?
how do I know it's a buffer join? I'll tell you in a second. So notice we have table access in memory full, or table access full, and no bloom filters. So that's more of a traditional hash join where we had to basically scan the date dimension table, created a probe table in the PGA, and then as we scanned the line order table, we had the probe, the date dimension table in the PGA. That's a traditional hash join. The reason we know that we didn't do any physical I/O is because it doesn't show up in our statistics for that query. So when you run a query in Oracle database, we'll keep track of not only the execution plan, but we'll also keep track of session level statistics associated with the work that was done during the query. And so each of these queries reconnects, so it resets the statistics, so you're seeing the statistics just for each of these queries. So basically we didn't do any I/O in the buffer cache to access all of that data. That make sense? You can try yourself, you don't have to trust me, but that's actually what's going on. So I don't think I have it because I didn't bring any slides. But if you go to, if you search on database in memory, Oracle database in memory, we have a blog where we have all sorts of information about this. We have white papers, we have documentation. There's a lot of information about database in memory. What I was trying to do was supplement what I had done earlier, talking to you guys with slides, and show you actually how this thing works. So if you're new to this, some of this might be kind of, well, okay, so it's pretty darn fast. Maybe I need to go back and take a look at some of that. Or if you were here before with some faces I recognize, then, oh yeah, okay, so now this is what it really looks like when you really run it. So we've done joins, multi-table, in this case, 2-table joins. The third area, so basically what we're doing is I'm leading you down the path of what database in memory leverages or uses under the covers to speed up SQL queries. So we talked a little bit about scanning data very, very fast, table access in memory full. I showed you a little bit about how we can push filter predicates. We can also push aggregations like mins, maxes, sums, function-based aggregations into the scan as well. I've shown you we can improve joins. And the third big thing that database in memory does is significantly improves group by aggregation. And that's really the three things that database in memory gives you is super fast scanning and aggregation and predicate pushdown, super fast join processing, and group by aggregation improvements. So that's what we're going to talk about next is group by aggregation. Then I'm going to go back to the IME, in-memory expressions, and talk about that and a little bit about some of the new features we've added to database in memory. Because as we've gone through 12.102, 12.2, 18C, now 19C, we've added additional features to database in memory. The core has stayed the same, but we've continued to improve it as we've gone along to make it even faster. So anyways, enough talking. So this will be our most complicated query. Whoops. Let's go back. So now we have the entire schema. We have our line order table. We have our 4 dimension tables. We're actually taking a look at the year, by nation, and the total profit. Joining these dimension tables to the fact table, the line order table. We have some filter predicates there. And notice we have a group by and an order by. And this particular query ran in 2 seconds, roughly. Now here's the fun part, at least for anybody who's worked with Oracle database. You won't see this with anything but database in memory. But the key here is you see something called a vector group by. So that's the third secret sauce or the third magic feature that got added in the database in memory and the optimizer, because it's the optimizer that chooses to do this. Normally you would see a hash group by or a sort group by if you're in a traditional Oracle database. We added this third ability to do a vector group by with database in memory. There's an entire white paper that discusses how vector group by works. Rather than using Bloom filters, we use key vectors. And the gist of this is we're able to do our join between all 5 of these 4 tables to our line order table, just as we did with Bloom filters. So we now turned hash joins, actually joins 4-dimension tables joining to the in-memory, to the line order table. We're able to do that all simultaneously, and there's some tricks that are used in the optimizer to do that, swap join inputs and write deep trees to achieve that ability. But the bottom line is we've taken and changed hash joins into scan and filter operations, and during that scan of that line order table, applying these key vectors, just like I talked about the Bloom filters, we're able to do the actual group by aggregation during the scan. So when we return from the scan of the line order table, not only have we done the join to the star schema, the 4 tables, the dimension tables, we've also done the aggregation. We're done with the aggregation at that point as well. So that gave us another 6 to 8x performance improvement over a traditional group by, not counting or with database in memory. So not only did we do database and memory very fast, but we actually were able to significantly improve the aggregation as well. We did all that in memory. So all this is processing in memory, and let's take a look at what it looks like in the buffer cache. So I have to tell Oracle not to do this, not to do that vector group by, because the optimizer says, well, that's the fastest way to do it. So I tell, well, you don't get to use it for this one. So we're going to run it. It already is taking longer than the 2 seconds we ran before that. I think it runs like 10 or 15 seconds. 21 seconds. So the only difference we had there was, well, the difference is we can't use vector group by, so we're doing a traditional sort group by. Remember I mentioned Oracle has the ability to do a sort group by, and then we introduced the ability to do a hash group by. So it's doing a sort group by, accessing those dimension tables and scanning the line order table all in the buffer cache. And we know we're doing it memory to memory, so 21 seconds versus 2 seconds, that's a huge impact. So the benefit of in-memory access, being able to change joins and do scan and filter operations, and then being able to do the aggregation during the scan processing. Again, didn't have to change the SQL at all. We put a hint in, but that was only to say don't use in-memory for this test. You wouldn't normally do that, but it's the same exact SQL. Your application doesn't have to change. If you're certified to run against Oracle database, whatever version 12.102 or higher, your application can take advantage of this. Now remember, this is analytic processing. We're scanning lots of data. So we're not going to speed up inserts, updates, and deletes DML processing, but this can significantly improve analytic performance within your applications. So it's like I went through that pretty fast, which is good. So I have a couple other things I want to describe to you. So all of this is basically CPU accessing memory, running a SQL execution plan, and returning results. So there's no I/O involved, either in the row store, because we artificially populated the buffer cache as well, cached that data. We populated the data in the column store, but the column store is way faster, so let's forget about the row store. So hopefully you're convinced that the column store is a good thing, provides significant performance improvement. So the question then becomes, how do you get faster than that? How do you improve it? So the only two ways that I can think of, and that if you think computer science, you've either got to parallelize or you've got to reduce your CPU footprint to speed up existing queries that are now using these operations to use CPU to access the data in memory. So those are your two choices, unless you can come up with another one. We're no I/O, we're not changing data, so we don't have serialization issues. We're literally scanning data in memory using CPU. So we already support parallel query. Oracle databases had parallel query for a very long time, since 7.1 maybe? I'm trying to remember. A long time, Oracle 7. We actually use parallel query when we distribute the data in the column stores in rack, and I described that in the last session I was here. But in addition to that, we implemented a new feature called in-memory dynamic scans. So we can actually dynamically control this scanning in parallel. So that's one way to speed things up. The other thing I was going to show you, though, which is much easier to show, is something we call in-memory expressions. And I had a query here. And notice that this query it's selecting ship mode, summing the order price, and then it's doing this arithmetic expression, looking for the discount price. Basically, we're taking order price, subtracted from order price times the discount, and adding tax to it. So we're basically doing an arithmetic expression there. And this query ran in 15 seconds. We accessed in-memory, the data in-memory table access in-memory full, and we did a bunch of work. So, this is another enhancement that came out in 12.2. So we did something we call in-memory expressions. So you can actually see I've already created them. all I did was I basically created a virtual column. Notice that right there is that arithmetic expression right there. So that guy right there. So I said, all right, rather than having an application do the same processing over and over and over again, why don't we take commonly used expressions and just materialize them in the column store? So they will only do it once. I mean, the fastest way to do something is to only do it once. The next fastest way to do something is only, is not to do it at all. The next fastest way is just to do it once. So let's just do it once. And we'll materialize that expression. You can do this manually, like with an alter table command, or the optimizer will actually keep track of commonly used expressions, something we call the expression statistics store. And this goes back loosely to some of the autonomous stuff we've been working on that you've probably heard about, but not to get onto the marketing end of the thing, but the bottom line is who better to know what commonly used expressions are than the database itself, because it's the one running all the queries. Just like we have heat map, and what we do is keeping track, we're now working on keeping track of populating the most beneficial objects that will take advantage of database and memory automatically using something we call heat map. So we've been working a lot on automating the manageability of the database and, in our case, database and memory. So anyways, so I had already previously created this column, materialized this arithmetic expression. Nothing in life is free, so it does take up space in the column store. There's just no way around that part. That's the in-memory part. So what's the difference? Does this make any difference in? So let's actually run this thing. So now what I actually did. Sorry, I should explain that. I cheated a little bit. I put in a command here to disable the use of an in-memory expression. So in Oracle, once you create something, if it's faster to use it, that's what we're going to do. So for these kinds of tests that show you what's the difference, I got to do things to disable the use of it so that I can show you the difference. And so we didn't use this because I disabled it, and I can prove it. Maybe if I can get my thing to work here. Nice scroll. Notice in the statistics, I talked a little bit about statistics and shows you what work occurred during the running of the query. Just keep in mind that you don't see anything about in-memory expressions there. Going the wrong way, sorry guys. So let's run that query, same query, without my little trick to defeat it. Same exact query. The previous query ran in 15 seconds. And this query ran in 7 seconds. So we cut half the time out of this query. So how did we do that? Same exact execution plan, table access in memory full. We're looking at the same rows, columns I should say, column values. But now what we see, in addition to our previous statistics, is we see this stuff. And all this is, you don't have to know this. This is just for the gearheads who want to dive in and see, did I take advantage of certain features? But when I created that virtual column and populated it in the column store, it took up space, we stuck it in something we call an IMEU, or in-memory expression unit. And so now we see in our statistics that not only did we access the 111 IMCUs, but we accessed 111 IMEUs in addition to that. So we actually used IMEUs, and notice that our CPU time went half. And so by not having to recompute that expression, and it's actually kind of surprising that a fairly simple arithmetic expression sucks up that much CPU. Normally, Oracle customers don't notice that because they've got so much I/O and contention going on that it's masked. But when we're now down to literally CPU and memory processing speeds, it makes a big difference. So that's the other half of parallelization and reducing the CPU footprint. We also have something called join groups, where we avoid having to recompute hash values constantly. Even with the ability to use key vectors or Bloom filters, we still have to create a hash value to check when we're scanning the data. So we have things like join groups. We have in-memory dynamic scans for parallelization and distance of parallel query. We have, we've extended the ability to use database in memory on data guard. We have automatic in-memory and automatic data optimization. So we've been working in the later releases not only on performance enhancements, but making it easier to manage what data. Because typically what the two things that Oracle customers ask is, well, how much memory do I need? And what objects do I put in the column store? Because it's a two-edged sword. We don't put, you can, but typically our customers don't have enough memory to put the entire database in memory. And you can put your entire schema in if you want. You can compress it to very high levels of compression. But if you don't have enough memory, then the choice is, well, what will be the biggest bang for the buck in my analytic processing? And so we're working on something called automatic in memory, using heat map to automatically populate, and we've already got this in 18C and 19C, to automatically populate objects that are the hottest, if you will, or the most active for analytic processing. And where we're headed with that is to make that completely autonomous and just take care of it all for you. We'll always give you the ability to do an alter table in memory, but the idea is, why not let the database, based on usage, decide what objects belong in the column store? So all of this, again, goes back to, all you have to do is enable this thing, and your applications can run much faster with the reporting parts of it, much, much faster. And one last thing I'll leave you with, since I think I'm almost out of time, is that the next question might be, in a mixed workload environment, what's the cost here? Because that's typically the DBA is going to say, well, oh my God, so I'm going to do this, but I have 2 copies, your question about 2 copies of the data, what's the performance penalty for that? And so we have actually a video out on our Database and Memory YouTube channel that shows we worked with the real world performance team who are the database hotshots, took an actual SAP OLTP workload, we don't say it's SAP, but it is, OLTP workload, doesn't matter, mixed workload actually, and then we added, so we ran that with and without database and memory, and we had consistent performance. Then we added analytic workload on top, and we did it with objects populated in the column store and without objects populated in the column store. And what we found, and this is why we say we can do this in real time on the source data, as long as you have CPU headroom, you can run any of your analytic workload with database and memory and not affect the performance of your OLTP workload. Again, as long as you have CPU headroom. Because remember, when we're only talking about CPU and memory access, we're not changing data, we're not having to serialize the data. So, but as soon as you invoke I/O on that analytic workload, everything kind of starts to fall apart. And that's what this video shows, if you're interested in taking a look at that. And that's why we kind of talk about, or I talk about a lot, real-time analytics, being able to actually now avoid having to maybe create a decision support system, maybe being able to run your business intelligence applications or your critical analytic applications right on your source data, and not having to wait for that data to be either transferred to a data warehouse, a data mart, maybe a decision support system. So true real-time analytics. As long as you've sized your CPU capacity, which is just a capacity planning problem, then you can take advantage of database and memory in real time. All right, so did that generate any questions? I know I'm kind of pushing up against the raffle time, so I don't want to.
I have some questions.
Yes,
First,
go ahead.
I'd like to know what is the minimum requirement for the memory to run this latest version, right?
So the minimum requirement for memory is 100 megabytes. So the column store has to be at least 100 megabytes in size.
Okay.
And then there is no maximum in essence, because database and memory lives within Oracle database, so the largest amount of memory footprint that Oracle database can address, database and memory is part of that, so we can address as well. And it's larger than any memory footprint you could put in a current machine, so it's effectively as large as you can stick in your machine.
The second question is there's any performance related to the numbers of CPU affect to the single query?
Sure.
I mean, so only the one query. That means is a special assign a CPU to that query, or is if there's a have to join, or maybe.
No, that's not the question I thought you were going to ask.
Right.
What I thought you were asking was, if I have a slow CPU and a fast CPU, what's the difference in speed of the query? So we got that.
You don't have to power enough the CPU.
So Oracle database runs on top of the OS, right? So we're at the mercy of the OS scheduler. So as long as you have, as long as your process can be scheduled on the CPU, it's gonna run. Is that where you're headed?
No, that means you run as a single CPU. You will have multiple
So in
CPUs
Oracle,
there.
so Oracle runs both serial queries and parallel queries. So if you're running a serial query, you'll effectively be running in a single foreground process.
Okay.
So you'll run on one CPU at a time.
Okay,
You know,
I see.
you'll be given the Linux or whatever OS schedule you're running. You can also parallelize a query in two ways in database and memory. You can use parallel query, so the query can be parallelized both across a single instance or a rack node, rack cluster. And in addition to that, we also support something called in-memory dynamic scans, where that scan, that table access in-memory full, can actually be dynamically parallelized. That scan can be dynamically parallelized in addition to what we do with parallel query. Remember I said the two ways to speed something up would be parallelize it or reduce the CPU footprint. And Oracle Database supports actually, with database and memory, two ways to parallelize that query.
I see. Last question.
Yeah.
In your presentation, that mentioned security risk. If, like, say here, so I have encryption, some fields are root field, or maybe it's a colon. So how does handle this situation?
So that's actually an Oracle database question, so let me tackle it from that standpoint, and then I'll just fill in what database and memory does. So Oracle database supports two levels of encryption. Transparent data encryption, where we encrypt it on disk, but then when we read it into memory, we unencrypt it. So it lives in memory unencrypted, but it lives on disk encrypted. So that's one form of encryption. That's Oracle database, has nothing to do with database and memory per se.
So you're saying that in memory, for this scenario, it's always get the decrypt in the memory.
If you're using transparent data encryption, yes.
Okay.
Now we also support column level encryption. So in addition to encrypting it on disk, you can encrypt the column or columns in memory as well, buffer cache or database in memory. The risk or the problem with that is that if you're trying to do analytics on those encrypted columns, that means we have to unencrypt them before we can do that.
Right.
So typically what happens is those encrypted columns are made payload columns. In other words, they're sensitive columns, but they're not typically the ones you're directly doing analytics on with filter predicates. So there you get kind of the best of both worlds in the sense that we get the column values back that we're interested in, and then those that are encrypted can be decrypted and then returned back to the application. So and both of those are Oracle database features, not database and memory. We just run within Oracle database, like same as we take advantage of things like parallel query, data guard, rack, all of it. If you're using Golden Gate, none of that is affected or does database and memory prevent you from making use of.
Cool, thank you.
Sure. Any other questions? Well, great, thank you very much. I think I wanted just so you can